In order to understand the electrical impulses that are generated at the SA node, we need to understand how action potentials are generated at the SA node. So we call this a nodal action potential. Here's the graph. The x-axis we have time in seconds, and in the y-axis we have membrane voltage in millivolts. Let's make a few important points. Minus 60 millivolts, minus 40 millivolts, 0 millivolts, and plus 30 millivolts. The minus 40 millivolts is important because it is the threshold voltage. If you remember, the threshold voltage is the minimum voltage needed to trigger an action potential. At minus 60 millivolts, voltage-gated sodium channels open and sodium flows in, causing a depolarization. At minus 40, voltage-gated calcium channels open, and at plus 30, voltage-gated potassium channels open, producing an action potential. From minus 60 to minus 40, we call it the pacemaker potential. This is in the place of a resting membrane potential, which the heart does not have. It has a pacemaker potential in the SA node. So the action potential has a depolarization phase and a repolarization phase. The depolarization phase is caused by calcium, and the repolarization phase is caused by potassium. So let's review this. The pacemaker potential is caused by slow sodium inflow, depolarization by fast calcium inflow, and repolarization by fast potassium outflow. Together we have an action potential. Whenever you exercise, your heart rate goes up. This is because the sympathetic nervous system is turned on and it acts on the SA node, causing it to raise the heart rate. So let's see how that happens. Here we have sympathetic stimulation of the SA node. This causes the permeability of the calcium and sodium channels to go up. So the permeability, meaning the calcium and sodium channels, open more, and so this increases the movement of sodium and calcium. Therefore, there is fast inflow of calcium and sodium. Even though sodium is normally slow, it's a little bit faster. And this increases the rate of depolarization. So there are faster depolarizations within the same time frame. So we end up with more action potentials within the same time frame. So the number of action potentials goes up. So if that goes up, the heartbeats per minute goes up as well. So number of beats per minute goes up. So that's the arrow going up, meaning it increases. And so the heart rate increases. Again, we use the arrow going up. So here we have it. Sympathetic stimulation of the SA node results in an increased heart rate. When a person is suffering from an anxiety attack, they have a very high heart rate. This is sometimes addressed by prescribing beta blockers, which have the ability to lower the heart rate. What a beta blocker does is to block the adrenaline receptors on the SA node. If you remember, adrenaline has something to do with the sympathetic nervous system. So it blocks essentially the action of the sympathetic nervous system on the SA node, or our pacemaker. So the beta blocker, here we have it, results in blocking adrenaline receptors on the SA node. Now adrenaline cannot bind to its receptor because it has been blocked by the beta blocker. Sympathetic stimulation of the SA node goes down. So we're going to use a down arrow to indicate decrease. This results in the permeability of the calcium and sodium channels to also decrease. So we will use the down arrow to indicate decrease. As a result, there is slow inflow of both calcium and sodium. Now, if there is slow inflow, there's going to be slow depolarization. So slow depolarizations occur. When this happens, you're going to have fewer action potentials in the same time frame. Fewer action potentials per minute. Fewer action potentials at the SA node mean fewer heartbeats per minute, resulting in a lowered heart rate. So there we have it. Beta blockers resulting in a low heart rate. The term arrhythmia means irregular heart rate. This can come in two forms: bradycardia, which means a slower than normal heart rate, or tachycardia, which is faster than normal heart rate. People with tachycardia are often prescribed calcium channel blockers that will lower the heart rate and bring it back to normal. So let's take a look at how calcium channel blockers lower the heart rate. Calcium channel blockers lower the permeability of calcium. So the calcium permeability decreases. We see the down arrow for decrease. This causes calcium inflow to slow down. The slow calcium inflow causes the depolarization to slow down as well. When the depolarizations are slow, we have fewer action potentials per minute. Fewer action potentials means fewer heartbeats. So we will have fewer heartbeats per minute, resulting in a lowered heart rate. Now, this is beneficial because the heart rate is going back to normal. So there we have it, a calcium channel blocker resulting in lowered heart rate.